Hi, I'm Tianyuan Jing from NUS. I'm glad here to present our work, Double Explore Then Commit Asymptotic Optimality and Beyond. This is a joint work with Pan Xu from UCLA, Xiaokui Xiao from NUS, and Quanquan Gu from UCLA. In unbounded problem, we have k arms and a time horizon t. Each time step, we need to pull an arm, and then we can observe a reward RT. Our aim is to find the best policy to minimize the regret. Here, the regret is defined as the expected difference over t time steps between playing the best arm and playing the arm according to the strategy. One of the most important metrics for regret is the asymptotic optimality. Lei and Robbins proves that when t approaches to infinity, the regret over log t is the least sum of 2 over delta I. Here delta I is the gap between the best arm and the i's arm. When delta I is known to the strateger, the regret can be 4 times smaller. There are lots of algorithms that prove to be asymptotic optimal, such as UCB, Thompson sampling, and Bayes UCB. However, all these strategies are fully sequential, which means that they need the outcome of each arm pulls at every time step. This is not suitable in real application. For example, in drag tests, there is typically a waiting time before the effects of the drags become observable. To solve this problem, we need to use the batch-banded model. In batch-banded model, the time horizon t is divided into a small number of batches. For the ith round, we pull all the arms in the ith batch, but the outcomes are only revealed at the end of the round. In batch-banded problem, the aim is to minimize the regret, but also the rounds. Previous work also studied the minimax regret in batch-banded problem. Besides, the algorithm they used is the ETC strategy. So a natural problem is that can ETC strategy achieve the asymptotic optimality? The ETC is the strategy with distinct exploration and exploitation stages. The reason that ETC can be easily extended to batch-banded problem is that the outcomes in ETC is only used to test if the stage switching condition is satisfied. Hence, it is possible to use a small number of rounds to find the stage switching time point. Unfortunately, the class of two-stage ETC proved to be suboptimal in asymptotic sense. A natural question is that, can a general ETC with more stages achieve the asymptotic optimality? We answer this question by proposing an algorithm with 2 exploration and exploitation stages. The algorithm achieves the asymptotic optimality. For simplicity, we use 2 unbounded problems to introduce our main idea. For the first stage, we pull all arms uniformly till the stage switching time satisfied. Then for the second stage, we let 1' be the arm with the largest average reward in stage 1 and pull it t1 times. The regret of the first stage then is bounded. After first 2 stages, the average reward of 1' is concentrated on mu1'. This is because that by setting t1 equals to log square t and event e be that 1' is concentrated on its mean, then it happens with high probability, and the regret caused by the opposite of event t is bounded by 2 over delta. While the 1' is concentrated on its true mean, we explore the 2' in third stage. Finally, we commit to the arm with the largest average reward. The difference between DETC and 2-stage ETC is that the error in 2-stage ETC from 2 arms. But in DETC, since the 1' is well estimated, the sampling error is only from the 2', hence the regret will be 2 times smaller. We further extend DETC to batched DETC algorithm and achieve a 1-round complexity. Moreover, we extend our DETC to DETC-M, where later achieve the asymptotic optimal and minimax optimal at the same time. We further extend to DETC to any time t and general k-arm settings. Thank you for your listening.